So today we're going to hit some specific properties of electromagnetic waves. And a lot of this is going to be very similar to properties that we've talked about for waves in general and for sound waves. There'll be a couple of specific things that we're going to mention that apply only to light waves. Okay, so when we think of properties of electromagnetic waves, a lot of times you'll see electromagnetic in place of writing all that out. Sometimes your book, and I will do this in some of the problems that I've written for you, I will abbreviate that as an EM wave. It stands for electromagnetic. It includes visible light, but it includes other types of electromagnetic waves as well, which we'll go into more detail in the next several days here. The speed of light in a vacuum we know to be 300 million meters per second. And when Einstein did a lot of his work on the theory of special relativity, which is way beyond the scope of high school classes, you wouldn't hit that till you got to college. But basically what Einstein discovered is that the speed of light in a vacuum, he called that the ultimate speed limit. Nothing can go any faster than the speed of light in a vacuum. And I'm not even going to begin to get into why that is true. Just understand that nothing is going to be able to go faster than this particular speed right here. Now, the speed of light is, or the speed of electromagnetic waves is not temperature dependent like sound is. You remember I gave you an equation for determining how fast the speed of sound was depending on what the temperature was. Well, for light, it doesn't matter what the temperature is, but as I mentioned in the last video, the speed of light is the slowest in solids and it is the fastest in gases. So if you didn't get that point down before, here it is again in case you needed to hear it again. Now, before when we've talked about waves, we know that the equation, the velocity equals the frequency times the wavelength. We discussed that extensively with sound. We did problems with it when we talked about waves. We're going to alter it just a teeny bit for light because the speed of light in a vacuum, Einstein gave that the variable c, and so I just substitute this c in for the speed of light, for velocity, for the speed of light. And so again, the speed of light is just equal to the frequency times the wavelength. And as we've discussed many times before, if the frequency goes up, the wavelength goes down. If the wavelength goes up, the frequency has to go down. Now, with sound, we said if the frequency goes up, the pitch goes up. With light, if the frequency goes up, the energy goes up. Now with sound, the energy was related to the amplitude of the wave. With light, the energy is related to the frequency of the wave. And so the higher the frequency, the greater the energy. Not all electromagnetic waves have the same energy. And again, that's something that in the next couple of days, we're going to get a lot more detail about that, about which kinds of electromagnetic waves have a lot of energy and which ones have lesser amounts of energy, because some electromagnetic waves have so much energy that they can be quite dangerous to us, and others are relatively harmless because they have so little energy. But that energy is all directly tied to the frequency of the wave. Because we're talking about light, and all electromagnetic waves are similar to light in some way, we can also talk about the intensity. Now, if you have a light bulb and you have the book that you're reading really close to the light bulb, the light's really bright. Obviously, if you pull the book away from the light bulb, the light isn't as bright, it's not as intense. And so we call that particular property the intensity of the light. The farther away you get from the source, the less the intensity is. And the relationship between the two of those is actually identical to the relationship we found in the universal law of gravitation. And that's that as you square the distance away that you get from the light source, the intensity goes down. So, for example, if I double the distance away that I am from something, so if the distance is going up by 2, that means the intensity is going to go down by a factor of 4 because I've got to take the double, the 2, and I have to square it in order to get 4. So if I triple the distance away from something, so if I'm 1 meter away and then I make it 3 meters away, if I triple the distance away I am from something, I'm going to square that 3. 3 times 3 is 9. So if I triple the distance, the intensity is going to go down by a ninth. Okay, now the other way I showed you to do that when we did the universal law of gravitation is that if it went down by a factor of 4, that means the intensity of 1/4 of what it was before. If it goes down by a factor of 9, then the intensity is 1/9 of what it was before. So you can take that, the fact that it went down by that factor, and just turn it into a fraction. Okay, so as you can see, the properties of electromagnetic waves are very similar to a lot of the properties of other waves that we have already discussed. Just a couple of specific things for light, specifically intensity, and then the energy being related to the frequency. And so the questions you answer today will help you solidify those concepts in your mind.